Hello everyone! How much do you think you can do with only two magnets and a long hair? What if I told you that I can measure Earth's magnetic field with only the three components? Well, I'm gonna do it right now. The principle of the measurement is the following. I'll do two experiments. First, with a compass, by measuring the period of oscillation of the needle, as shown here, I can deduce a relation between the magnetization of the needle, that I call M, and Earth's magnetic field tangential component, which I'll call BT, as you can see here. Now, with the second experiment, by approaching a magnet to a needle, as I'm doing right here using two magnets instead, it will change the equilibrium angle of the needle, which allows me to find a second equation between M and BT, so that I can solve for M and BT. Now let's start with the first experiment. The only issue is that I do not own a compass, but with a hair and a magnet, I can build one. The principle of a compass is that the needle lines up with the field lines of the magnetic field, because the needle is a magnetic dipole and the magnetic field exerts a torque on it. Here, the needle I use is actually another magnet, which is obviously a magnetic dipole. I tied the hair to the center of the magnet and tied the other end to a support. I add a frame of reference, and there we go, we've got a compass. Now let's find the first function we need. Using Newton's second law of motion and the approximation of the sinus, we prove a formula for the period. And there we have the first main equation. But we must not forget that it is only true when the angle with the equilibrium remains small enough. Therefore, I'll just disturb the needle a little bit. I'll record it with my phone and auto-track the position of the two white dots I put in the magnet. I export the data to Python, and boom, I have the angle in function of the time, from which I can deduce the value of the period. But J, the moment of inertia in the first equation, remains unknown. So let's measure it. I get the weight of the total magnet with a kitchen scale, and I take a picture of it to get the exact shape of it in Python so that I can calculate the volume, thus the density of the full magnet made of plastic and metal, so that I can deduce the distance d of the metal. Now, using a bunch of formulas involving the profile of the shape, I can find the moment of inertia of the full magnet using simple integrals. And finally, we know all the parameters in the first equation, and we are done with the first experiment. Now, let's find the second equation. The needle moves when approaching the magnet to it, because the magnet creates its own magnetic field, whose expression is known. It's only true when observing it from far enough, so I can't approach it too much. I'll keep a distance of at least 15 centimeters. I try to approach it from a perpendicular position to Earth's magnetic field, so that the magnetic field that the needle sees has two perpendicular components, Earth's and the magnet's. The angle of the needle will give us the impact of the new component relatively to the previous one, Earth's one. And combining it with the formula for the magnetic field of the magnet, we get the second main equation. Let's measure the angle alpha. The compass is very unstable. It never really stops moving, so I can't get an exact angle from a picture. I have to record a video, track the angle, and get the average angle, which is surprisingly extremely precise. As you can see here, I get almost the exact same value every time. With this method, I get the angle alpha, and with a ruler, I measure the distance between the two magnets. And there we go, we know all we need about the second equation. Finally, combining the two main equations, we get the final results for Earth's magnetic field tangential component and for the magnetization of the magnet. Using my smartphone, I get a value of roughly 12 microtesla, which is exactly the order of magnitude I got. The main uncertainty in my calculation comes from J, because I don't know the exact density of the metal and plastic. Overall, the results are pretty satisfying, and the experiment works pretty well. Thank you for watching. I hope you enjoyed the video. Goodbye.